In this video, we are going to be learning about barometers and manometers, which are devices used to make pressure measurements. A barometer is a simple device which has a vacuumed tube. That means there's no gas up here. So vacuum equals no gas. Or at least very, 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 very little gas. There's degrees of vacuum. So you try to remove all the gas in here so that as atmospheric pressure pushes down on this liquid, it gets pushed up into this tube because there's nothing pushing down this liquid. So this gets pushed up into this tube. We use mercury in barometers historically because mercury is a very dense material. And this millimeters of mercury unit literally came from measuring the height of this column of mercury in millimeters. So 1 atmosphere of pressure would make this column of mercury rise 760 millimeters, which is approximately 29.92 inches, which is a little bit less than 1 yard tall, 3 feet, a little bit less than 3 feet, 2.5 feet, 2.5 feet-ish. So that's a barometer, historical style. It was filled with mercury as opposed to a less toxic substance like, well, water, because mercury is a metal and it's very, very dense because it's a metal. So there's not really, like, at room temperature, the only liquids on the periodic table are mercury and bromine. And bromine has its own issues, and so they picked mercury. Mercury's toxic, though, so people don't want to play with mercury anymore. It's a lot of fun. But water, which is a liquid at room temperature, it's a lot less dense. And so a column of water would be 33.9 feet tall, and the mercury was only 2.49 feet tall. So that's 2.5 feet tall. That's like almost 34 feet tall. That's way less practical than that. A manometer is a similar-ish device used to measure pressure for a sample of gas. So instead of having a closed tube with atmospheric pressure pushing down on one end, we need to have our gas sample connected to one end of the manometer. There's a couple different styles of manometers. This one has a closed end, which is a vacuum, which is similar to what was on our barometer. And if you open up this gas pressure, all this gas is going to push down here. And if this side is not pushing down as much, then this side will be higher. With this closed end and a vacuum here, really there shouldn't be very much of anything pushing down. And so how high this goes really only depends on what the gas pressure is. So that's going to push down and that's going to cause that end to rise up. You'll notice here that the difference between this equation and this equation is this P atmosphere term. And so with this closed end here with the vacuum, there's no pressure due to the atmosphere because it's a vacuum. So that's what the difference in the equation is. You can almost think of it as a zero. So you have your zero plus your height of your column. The different symbols in here, height is H, density is the rho, that's the Greek letter rho, and then G is for gravity. So the height of this column here is going to depend on the density of the fluid, the force due to gravity, and so forth. Your pressure of your gas will depend on that. If you do have an open-end manometer, then you do have the pressure of the atmosphere pushing down on this. And so then you can measure your pressure of your gas relative to the pressure of the atmosphere. In this case, the atmospheric end is lower. That means that the atmosphere is pushing down more than the gas is. So this is a bigger downward force. So it's going to push that up, and that's not going to be pushing it down as much. So when we do this, we have to make sure that we know that our pressure of our atmosphere is more than our pressure of our gas. So we're going to be subtracting that height difference. Over here, the gas is pushing down more than the atmosphere. So the atmosphere is lower than the gas pressure. So we're going to be adding to make sure that we're increasing our atmospheric pressure. It might seem a little bit of intimidating to think of like height, density, and the acceleration due to gravity. And so it's much easier just to do all of your math in millimeters of mercury. Way easier. So here's an example of this type of manometer problem where we're asked to calculate the pressure of our gas. This problem reads, a sample of gas is connected to a manometer. The atmospheric pressure is 761 millimeters of mercury, and the gas end of the manometer is 42 millimeters lower than the atmospheric pressure side. What is the pressure of the gas? Well, conceptually, if this side is lower, then our pressure of gas is more than our pressure of our atmosphere. So we need to take, in order to calculate our pressure of gas, we need to take our pressure of our atmosphere and we have to add to it that height difference. We're going to make sure that our atmospheric pressure is in millimeters of mercury so that we can add those two units together. So we just add them together. So 761 plus 42 is 803 millimeters of mercury. Make sure you follow your addition and subtraction rule for sig figs. Both of those were significant to the ones place. Here's a practice problem for you. It reads, if the atmospheric pressure is 0.997 atmospheres, what is the pressure of the gas in kilopascals? Go ahead and pause the video and try to work this out, and unpause the video when you are ready to check your work. Okay, so in order to use this in millimeters, we need to convert this to millimeters of mercury. And then we'll need to get from millimeters of mercury into kilopascals because that's what it's asking for. So we're going to be paying attention to our units. We have to realize conceptually that this downward force is a lot different than this downward force. So our pressure of our gas is going to be equal to our atmospheric pressure. And then we're going to be subtracting out that height difference. So we have to get this to millimeters of mercury. So our P of our atmosphere is going to be equal to 0.997 atmospheres times 1 atmosphere is 760 millimeters of mercury. So 0.997 times 760 is equal to 757.72. I'm not going to round yet because I'm not done yet. I'll only round the final answer to a problem. I'm going to underline my sig figs though so I remember them. So now I can plug that back in to my P gas equation. 757.72 mmHg, subtract out my height difference in millimeters. And so that's going to be 734.72 millimeters of mercury. And then I need to convert that to kilopascals. So 734.72 millimeters of mercury. And I need to cancel out my millimeters of mercury. And I need to get into kilopascals. What the heck did I? Kilopascals. So there are 101.325 kilopascals for every 760 millimeters. So I can take that and multiply by 101.325 divided by 760. And that is equal to 97.954. And I need 3 sig figs, 1, 2, 3. So that's going to round up to 98.0 because that 5 is going to round up, make that a 0, and carry over the 1. So that's going to be 98.0 kilopascals.